Section 1 Introduction. We're here to discuss the challenges and advancements in evaluating natural language generation systems. As these systems continue to improve, assessing their performance becomes increasingly complex and crucial. Take machine translation, MT, for instance, a field where evaluation is of utmost importance. Traditional automatic metrics like BLEU, which measure the surface-level quality of translations, are becoming less reliable as the systems improve. They often don't align with human judgments anymore. To keep up with the ever-improving MT output, a new generation of automatic metrics is quickly emerging. These metrics, which are fine-tuned using human judgments, currently represent the best in automatic evaluation benchmarks. However, they usually provide a single, non-explanatory quality score, making it hard to understand the nature and extent of errors they detect. This lack of insight makes it difficult for developers to use these metrics to enhance their systems. Contrarily, advanced human evaluation methods like multidimensional quality metrics provide more detailed feedback. They ask professional annotators to identify and label error spans with a category and severity. This comprehensive feedback can help us better understand the model's limitations and improve it. In this study, we explore whether large language models, LLMs, combined with a few human annotations, can be used to create an automatic metric that provides detailed feedback similar to human experts. This idea is inspired by recent studies showing that LLMs can be used as automatic metrics to generate a single quality score. However, previous research has mainly focused on score prediction, without considering the use of any annotated data, and only in languages with abundant resources. We conduct a large-scale study of LLMs' capabilities for machine translation evaluation, both with and without a reference translation. We also compare prompting and fine-tuning methods and investigate their performance in low-resource scenarios. Building on the idea that LLMs' performance can be improved by prompting them for rationales of their predictions, we propose AutoMQM. This is a prompting technique for mount evaluation that asks LLMs to identify error spans in a translation and classify these errors according to the MQM framework. The quality score is then automatically derived from the identified errors. AutoMQM's main advantage is its interpretability, as users can inspect the errors responsible for a score. Our study confirms that LLMs are excellent system-level evaluators, but they show low correlation with human judgment compared to learned metrics at the segment level. We also find that fine-tuning an LLM with human judgment improves its low segment-level performance, showing similar correlations with human judgment at both the system level and segment level to state-of-the-art learned metrics. We are the first to evaluate LLM-based evaluation methods on low-resource language pairs. Their performance is promising, but still falls behind state-of-the-art learned metrics. With AutoMQM, POM2 models can be prompted to generate detailed MQM-like annotations, outperforming their score prediction counterparts at the segment level. These models correctly identify over 50% of words that are part of major errors, comparable to the ones produced by state-of-the-art supervised word-level evaluators. Our findings could have significant implications for not only mount evaluation, but also the evaluation of machine-generated text in general. They further highlight the potential of using LLMs to provide AI feedback. Section Summary. The evaluation of natural language generation systems has become increasingly challenging as their output quality improves. While automatic metrics like BLEU are becoming less reliable, learned automatic metrics that leverage human judgments show high correlation with human evaluations. In this paper, we explore the use of large language models, LLMs, combined with human annotations to design an automatic metric that generates rich feedback similar to human experts. We confirm that LLMs are state-of-the-art system-level evaluators, but show low correlation with human judgment at the segment level. However, fine-tuning LLMs with human judgment improves their performance, and our proposed AutoMQM technique allows LLMs to identify error spans and classify errors, providing interpretable feedback. Section 2 Background. Mount evaluation. We're going to delve into the background of machine translation evaluation, a topic that has been extensively researched within the field of natural language processing, NLP. The task involves assessing the quality of a translated sentence from a source language to a target language. The evaluation metric gauges how well the translated sentence captures the meaning of the original sentence, while also considering factors like fluency. This task is challenging due to the vast number of potential correct translations for any given sentence, and the fact that these translations can't always be predicted in advance. To make this task more manageable, a reference translation, usually created by a professional human translator, is often used as a benchmark when evaluating the translated sentence. This approach is known as reference-based evaluation, as opposed to reference-less evaluation or quality estimation. In the past, the primary goal of human evaluation of machine translation was to assign a single quality score to a translated sentence. As a result, learned metrics, which use collected human judgment data, were trained and evaluated based on their ability to predict this score. These metrics have been successful in achieving high correlation with human-provided scores. However, this approach of viewing machine translation evaluation as a score prediction task has its drawbacks. Any scoring or ranking of translations inherently involves identifying errors in the translated sentences. Asking evaluators to only provide a single score can lead to hasty and inaccurate judgments. This realization led to the adoption of the multidimensional quality metrics (MQM) framework as the gold standard for evaluating machine translation. The MQM framework requires human evaluators to identify and categorize errors in translated sentences based on various dimensions, such as fluency and accuracy. Notably, the MQM framework doesn't require evaluators to provide a quality score for each translation. Instead, it automatically generates one based on the identified errors and their classifications. Despite the comprehensive nature of the MQM framework, most automatic metrics that use MQM data only utilize the final quality score produced by the framework, disregarding the information about the identified errors and their classifications. Section Summary. Machine translation evaluation is a well-studied problem in NLP, where the quality of a candidate translation is assessed based on how well it conveys the meaning of the source sentence. To simplify this evaluation, a reference translation is often included. Traditionally, human evaluation involved assigning a single quality score to a translation, but this approach has limitations. The multidimensional quality metrics (MQM) framework has been adopted as the gold standard, which asks evaluators to identify error spans and classify them according to various dimensions. However, most automatic metrics only use the final quality score and discard the error span information and classification. Section 3. Related work. We've seen the effectiveness of machine translation metrics that are learned and fine-tuned using neural network models. These models are trained on large volumes of unsupervised data, and their success underscores the value of transfer learning in creating metrics that align more closely with human evaluations. Recently, generative language models have shown remarkable results in understanding natural language and in zero-shot and few-shot transfer. This has sparked interest in using these models for evaluating translations. The use of GPT models for assessing machine translation tasks was first explored, revealing their potential as zero-shot evaluators. Since then, the use of GPT-based evaluation has been expanded to other generative problems. It was first pointed out that MQM annotations could be used to enable pre-trained models to predict major and minor errors. Like AutoMQM, these identified errors were used to automatically score translations. However, this approach depended on weaker encoder-only or encoder-decoder language models, required supervised data to function, and generally did not perform as well as other top metrics. We use their MA-T-ACE metric for comparison in our experiments. It was shown that error analysis, a technique similar to AutoMQM, could improve ChatGPT-based evaluators. However, they still depended on the language model to provide a score once it identified errors, rather than doing it automatically using a framework like MQM. Moreover, they only provided a very limited meta-evaluation using just 40 examples per language pair. At the same time as our work, InstructScore was proposed. This is a llama-based evaluator that asks models to identify and categorize translation errors, as well as provide a natural language explanation for each error. However, the authors only explored a model with 7 billion parameters and did not utilize the zero-shot and few-shot capabilities of models as we do in our work. Instead, they relied on a more complex approach of distilling the knowledge of a more capable GPT-4 language model. Additionally, WMT word-level quality estimation shared tasks use MQM data by converting span-level annotations of errors, usually of major severity, to word-level tags. Task 2 in the WMT19 quality estimation shared task evaluation specifically evaluated submissions of span-level annotations, although most submissions still consisted of models that predicted word-level tags which were converted to spans. We also compare against top-of-the-line word-level quality estimation models. Section Summary. The use of transfer learning in machine translation metrics has been successful, particularly with the use of pre-trained neural network models. Generative language models have also shown promise in natural language understanding and transfer tasks, leading to increased interest in using them for translation evaluation. Previous work has explored the use of GPT models and error analysis techniques for evaluation, but they have limitations such as reliance on supervised data and underperformance compared to other metrics. Our work compares against these previous approaches and also considers the use of word-level quality estimation models. Section 4. Using LLMs to predict quality scores. In this section, we delve into the use of large language models, LLMs, for predicting quality scores, a method that has been gaining traction in recent natural language processing, NLP, tasks, including evaluation. We're particularly interested in how these models can be applied to evaluate machine translation through score prediction. Firstly, we look at the concept of prompting. Essentially, we're testing how far we can stretch the capabilities of LLMs using only prompts. We define the task of machine translation evaluation and quality estimation using textual templates. These templates provide a general outline of the problem and have slots for inputs and outputs. This allows us to use LLMs for these tasks without making any changes to the model parameters. In this paper, we've chosen to use the Gemba SQM prompt. This prompt asks the models to generate a score between 0 and 100. We chose this prompt for two reasons. First, our initial tests with this and other prompts showed that it generally performed well. Second, using a single prompt allows us to make a fair comparison between different models. Although this prompt wasn't the best for system-level evaluation, it gave the best segment-level performance in Gemba. Next, we discuss in-context learning, ICL, an interesting feature of LLMs. These models can improve their performance on tasks based on prompts by including a small amount of labeled data in the prompt or context, without any changes to the model parameters. This technique is known as in-context learning. We're interested in how ICL affects the ability of LLMs to evaluate translation quality. Previous studies have shown that the effectiveness of ICL is closely linked to the specific examples included in the prompt. If the selection process for these examples is poor, it can lead to no improvements or even worse performance than without using any examples, the zero-shot case. Therefore, we explore two methods for selecting in-context examples from a preset pool of translation quality assessments: uniform sampling and stratified sampling. In stratified sampling, the pool of examples is divided into groups based on score ranges, and examples are selected from each group. Section summary. Large language models, LLMs, have been proven to be versatile and can be used for various natural language processing tasks, including evaluation. In this section, the authors explore how LLMs can be used for machine translation evaluation by defining the task as textual templates and using LLMs to perform these tasks without any parameter updates. They also investigate the impact of in-context learning, ICL, on LLMs' ability to assess translation quality, finding that the selection procedure for in-context examples is crucial for improving performance. Section 4.2 Fine-tuning. We've previously seen that large language models, LLMs, can perform tasks without any prior specific training, a process known as zero-shot evaluation. However, we haven't yet explored how much we can improve LLMs' performance by fine-tuning them using human judgment data. In a recent competition, the WMT22 metrics shared task, all the top entries were learned metrics, meaning they were pre-trained models that were fine-tuned using human judgment data. But these models aren't typically considered LLMs. So, we decided to investigate if LLMs could also be fine-tuned using human judgment data. The LLMs used in the top-performing metrics are generally much larger than the pre-trained language models used by previous learned metrics, which usually have less than 1 billion parameters. Additionally, most learned metrics use pre-trained encoder-only models, rather than decoder-only prefix language models. We decided to experiment with fine-tuning LLMs using two objectives. 1. Regression, R. This is a common method used for training learned metrics. The goal here is to minimize the difference, or loss, between the continuous scores obtained from the model and the human scores. This is often done using a method called mean squared error. 2. Generative classification, GC. In this method, we categorize scores into discrete classes and treat the machine translation evaluation task as a text-to-text classification problem. While it's important to produce quality scores that correlate with human judgments, metrics that only predict scores can be hard to interpret. For example, if a metric assigns a low score, it's not clear which parts of the translation were responsible for the low score and need to be corrected. This is especially problematic when the metric assigns an incorrect score to a translation, as it's much harder to understand why the evaluation model made a mistake and how to prevent similar mistakes in the future. In fact, reducing translation quality to a single score has proven problematic even for human annotators. Asking raters to only provide a single score can lead to rushed and noisy judgments. The current gold standard for translation quality evaluation involving human annotators is instead based on methodologies like the MQM framework, which provide richer feedback by identifying error spans, categorizing them, and evaluating their severity. Interestingly, another emerging trend in LLMs is the success of chain-of-thought prompting. This is when we instruct the model to produce a series of intermediate reasoning steps before generating an output. This often improves the performance on the task at hand. Furthermore, this chain-of-thought prompting can be used to obtain structured rationales from LLMs, which can lead to better performance than with free text rationales. Motivated by these findings, we propose AutoMQM, a prompting technique for translation quality assessment that instructs LLMs to identify errors in a translation and categorize the type of error according to the MQM framework. We don't ask the model to produce a score, as the MQM framework provides a procedure to obtain one from identified errors. The total score is the sum of penalties for all errors identified, where major errors are penalized with -5 and minor errors with -1. However, obtaining meaningful AutoMQM results in a zero-shot setting is a substantially more challenging task compared to score prediction. We found that, without any in-context examples, LLMs tend to produce outputs that are either uninformative or difficult to parse. Thus, we only consider the AutoMQM task in the few-shot scenario. Based on our findings, we explore the impact of in-context learning by sampling from the example pool using stratified sampling extended with a set of rejection criteria. This ensures that the example set has a balance between major and minor errors as well as diversity in the categories of errors. Section Summary. The section explores the potential of fine-tuning language models, LLMs, on human judgment data to improve their performance in translation quality assessment. It compares two objectives for fine-tuning LLMs: regression, which uses continuous scores, and generative classification, which categorizes scores into discrete classes. Additionally, the section introduces AutoMQM, a prompting technique that instructs LLMs to identify and categorize errors in translations based on the MQM framework, providing a more comprehensive evaluation than a single score. However, meaningful results in the AutoMQM task require in-context learning and are only considered in the few-shot scenario. Section 6 Experiments. In this section, we'll discuss the experiments we conducted and the data we used. We evaluated our metrics on both high-resource and low-resource language pairs. The high-resource language pairs we used were English to German, Chinese to English, and English to Russian, all of which were sourced from the WMT22 metrics shared task. We used MQM ratings to derive the ground truth translation quality scores. These ratings are given by expert annotators who mark errors in the translations and assign them different severity levels, which are then converted into a numerical score. For the low-resource language pairs, we used English to Gujarati and English to Kazakh from the WMT19 metrics shared task. Since MQM ratings aren't available for these pairs, we used direct assessment (DA) scores as the ground truth quality scores. These scores are given by non-expert raters on a scale from 0 to 100 and then normalized per rater. In our experiments, we needed in-context examples with MQM annotations for AutoMQM to work. Therefore, we limited our evaluation of AutoMQM to English to German and Chinese to English, as we had available MQM ratings from the WMT21 metrics shared task that we could use as in-context learning example pools. We based most of our experiments on two language learning models, LLMs, PaLM and PaLM2. PaLM is a 540 billion parameter autoregressive transformer model trained on 780 billion tokens of high-quality text. It has shown impressive performance on a wide range of NLP tasks, including machine translation. PaLM2 is the successor to PaLM and includes improvements such as compute optimal scaling, a more multilingual and diverse pre-training mixture, and architectural optimization enhancements. We mainly used two model sizes in the PaLM2 family, PaLM2 Bison and the larger PaLM2 Unicorn. We also explored the impact of instruction tuning by using a unicorn model fine-tuned on the FLAN dataset. For score prediction, we compared PaLM and PaLM2 against the GPT family of LLMs using the results and outputs from the Gemba evaluator. We evaluated the performance of AutoMQM with only PaLM2 models, which performed best in score prediction. For the high-resource languages, we compared our results to two strong baseline evaluation metrics, metric XXXL and Comet22, which were the top-performing metrics in the WMT22 metrics shared task. Both of these metrics are fine-tuned regression models trained on DA data from WMT, with metric XXXL initialized with Mount 5 and Comet22 with XLMR. In the AutoMQM experiments, we also compared our results to Matisse, a submission to the WMT22 metrics shared task that fine-tuned an XLMR model to identify major and minor errors and computed a score automatically. We also compared our results to the top submission to the WMT22 word level quality estimation shared task, word level Comet Kiwi, Comet WL, which is based on an XLMR model trained on a combination of sentence and word level data. We ran this model on the WMT22 metrics shared task data and converted the predicted word level OK, BAD tags into spans, considering a span as any maximal consecutive sequence of words marked as bad, assigning every span the major severity. Section Summary. In our experiments, we evaluate the metrics on both high resource and low resource language pairs. The high resource pairs are n-right-arrow-d, j-right-arrow-n, and n-right-arrow-ru, while the low resource pairs are n-left-right-arrow-gu and n-left-right-arrow-kk. We use MQM ratings for the high resource pairs and direct assessment, DA, scores for the low resource pairs as ground truth quality scores. We also compare the performance of our AutoMQM model with PaLM and PaLM2 LLMs against other strong baseline evaluation metrics such as Metric XXXL, Comet 22, Matisse, and Comet WL. Section: Fine-tuning. We've fine-tuned our model in two ways, for regression and for generative classification. In the regression approach, we used a real-valued logit, taken from a specific index in the first target token's logit vector, as the quality signal. This method was used to train our model, Metric XXXL, for the WMT 2022 shared task. The model was trained using WMT direct assessment data from 2015 to 2020. For generative classification, we divided the scores in the training data into 5 classes, ensuring each class had an equal number of examples. We then assigned verbal ratings to these classes, ranging from very bad to very good. To evaluate the model, we converted the predictions back into numerical labels from 1 to 5. Any predictions that didn't match a label were considered invalid and assigned a 0. We tested this fine-tuning approach on both direct assessment and MQM 2020 data, with the latter showing slightly better results. We also explored the effect of model size by fine-tuning 2 smaller versions of our model, which we named S and M. We compared their performance both with and without fine-tuning. The quality of an automatic evaluation metric is determined by comparing its scores with the actual quality scores on a large number of translations from various machine translation systems. This process is known as metric meta-evaluation. We used 3 different agreement scores in this work. The first is system-level accuracy, which calculates the percentage of system pairs that are ranked the same by the metric and the actual scores, averaged over a set of language pairs. System-level scores are defined as the average score across all segments. At the segment level, we used Kendall's tau, a standard correlation measure used by WMT. However, recent studies have highlighted issues with Kendall's tau, particularly when it comes to ties. In response, we recommend using a pairwise accuracy score, which rewards metrics for correctly ranking translations and predicting ties. This score, denoted as ACC*, ranges from 0 to 1, with a random metric achieving 33% accuracy. In addition to this, we also used Pearson's rho, a measure of the strength of the linear relationship between 2 variables. This is a complementary signal to rank-based correlations and is one of the standard correlations reported in WMT. Section Summary. For regression fine-tuning, a real-valued logit is used as the quality signal, extracted from a fixed index in the first target token's logit vector. Generative classification involves bucketing scores into 5 classes and mapping them to verbal ratings. The quality of an automatic evaluation metric is estimated through metric meta-evaluation, which includes system-level accuracy and segment-level correlations like Kendall's tau. However, a pairwise accuracy score is recommended, along with tie calibration, to address inconsistencies and biases related to ties in the metrics. Section: Span Meta-Evaluation. We're going to discuss the evaluation of our AutoMQM system, which not only provides scores but also identifies error spans. We can compare these predicted spans with the errors marked by annotators in the MQM annotations. We use 2 measures to evaluate the quality of these predicted spans. 1. Span precision, SP, which measures how much the predicted spans overlap with the actual, annotated, spans. 2. Major recall, MR, which measures the percentage of major errors that were correctly predicted as errors, regardless of whether they were minor or major. To explain this more simply, let's consider the set of actual spans, which we'll call S*. Each span in this set is a sequence of words. We'll denote a subset of S* that contains only the major errors as S*maj. Given a set of spans S, we define its positional set phosphorus monosulfide as the set containing the positions of all the words in every span in S. For instance, if a span starts at the nth position in the text, its positional set will include the positions from n to n plus the length of the span minus 1. Then, for a set of predicted spans, which we'll call hat S, SP and MR are defined as follows. SP of hat S equals the size of the intersection of P, hat S, and P, S star, divided by the size of P, hat S. Mr. of hat S equals the size of the intersection of P, hat S, and P, S star maj, divided by the size of P, S star maj. In simpler terms, we care about overall precision because we want to ensure that predicted errors are also marked by annotators. However, for recall, we're mostly concerned with major errors, as these have a larger impact on translation quality and are more critical to identify. We also report the Matthews Correlation Coefficient, MCC, which is one of the official metrics in the word-level quality estimation tasks. Now, let's discuss the results of our meta-evaluation. We found that almost all zero-shot language model evaluators performed better at the system level than learned metrics. However, at the segment level, the results were more mixed. None of the language models we explored was able to consistently outperform the baseline learned metrics. Interestingly, instruction tuning with FLAN seemed to decrease performance. However, this might be a problem with the FLAN dataset and not instruction tuning in general, as the GPT models are also instruction tuned and perform well. Despite these findings, the POM2 models achieved high correlations with human judgments, and the reference-less POM2 Bison was competitive with the learned baselines, particularly at assessing alternative translations of the same sentence. When comparing POM2 models with GPT-based Gemba Evaluator, we found that both types of language models performed similarly. However, POM2 models had higher system-level performance than GPT-based Gemba, while Gemba achieved better segment-level accuracy, particularly in the reference-less setting. We also found that, despite being prompted to give a score in the 0 to 100 range, these models almost always output one of a very limited set of scores, e.g., 0, 50, 90, 95. This seems to be a consequence of the pre-training objective. Section Summary. The section discusses the evaluation of predicted error spans in the AutoMQM system. The evaluation measures include span precision, SP, and major recall, MR, which assess the overlap between predicted and annotated error spans. The section also mentions the Matthews Correlation Coefficient, MCC, as an additional metric. In terms of system-level performance, zero-shot LLM evaluators outperform learned metrics, with POM 540B and POM2 Unicorn achieving the best results. However, at the segment level, LLMs struggle to consistently outperform the baseline learned metrics. POM2 models show high correlations with human judgments and perform similarly to GPT-based Gemba evaluators. Section: Fine-tuning. We've discovered that even though language learning models, LLMs, already perform exceptionally well in a zero-shot setting, their performance can be further enhanced through fine-tuning. This improvement is especially noticeable in reference-less evaluators, where a fine-tuned model called POM2 Bison outperforms others in segment-level correlations and matches the system-level accuracy across all language pairs. Interestingly, we noticed a trend when we examined how performance changes with the number of parameters. Smaller models, which aren't very effective as zero-shot evaluators, can achieve competitive performance when fine-tuned. Their performance only slightly decreases compared to larger, fine-tuned models. We also studied the impact of in-context learning, which involves increasing the number of in-context examples. Despite the known benefits of in-context learning for many tasks, we were surprised to find that including in-context examples during evaluation didn't improve performance, regardless of whether we used uniform or stratified sampling. To understand why in-context learning didn't perform as expected, we examined how specific sets of in-context examples influenced the scores generated by LLM-based evaluators. We found that the distribution of scores was heavily influenced by the scores in the in-context examples. For instance, even though the model never predicted a score of 79 in the zero-shot setting, it started to dominate the model predictions when a single example with that score was included. This suggests that LLMs might be overfitting to the specific scores provided as examples, rather than generalizing to the broader evaluation task. This could explain why in-context learning didn't perform as well as we expected. Section Summary. Fine-tuning language models, LLMs, can further enhance their performance in segment-level scores, especially for reference-less evaluators. Smaller models, although not effective as zero-shot evaluators, can achieve competitive performance when fine-tuned, with only a slight decrease compared to larger models. In-context learning, despite its benefits in many tasks, did not lead to improved performance during evaluation, as LLMs tend to overfit to specific scores provided as examples rather than generalized to the broader evaluation task. Section 6.3 Low Resource Languages. In this section, we discuss the performance of our PaLM-2 models in predicting scores for translations in languages with limited resources. We found that these models, like those for languages with abundant resources, are effective evaluators even without prior exposure to the language, achieving system-level accuracies of around 90%. However, these models do not perform as well as learned metrics, even when those metrics have not been exposed to data in these low-resource languages. We also examined the performance of the PaLM-2 Bison model with AutoMQM, a method that increases the number of in-context examples. Unlike with score prediction, we found that performance with AutoMQM generally improves as the number of in-context examples increases, up to 4 examples, after which it levels off. Furthermore, the variation across different sets of in-context learning examples seems to be lower, with most sets showing less than a 0.05 Pearson difference from the best performing sets. This suggests that evaluators for low-resource languages are more resilient to the choice of in-context examples when using AutoMQM rather than score prediction. We also found that the behavior of in-context learning is quite similar for both reference-based and reference-less evaluation tasks. Moreover, the sets of examples that perform well for one task generally also perform well for the other, with performance on both settings being highly correlated when using a fixed set of in-context examples. We then compared the performance of the PaLM-2 Bison and Unicorn models when prompted with AutoMQM. We found that prompting low-resource language models with AutoMQM leads to significant improvements in evaluating machine translation quality, especially for larger models. For instance, the Unicorn model performs better across all evaluations with AutoMQM than with score prediction, and its reference-less version is competitive with the best learned metric even at the segment level. However, for the smaller Bison model, the benefits of AutoMQM are less clear, with both techniques performing comparably. This suggests that scale is necessary for zero and few-shot fine-grained evaluation, like with AutoMQM. We also found that the distribution of scores produced by low-resource language models prompted with AutoMQM is much closer to the ideal MQM distribution, with models outputting a much larger set of scores, and in the same ranges as human annotators do. Finally, when evaluating the error spans produced by low-resource language models prompted with AutoMQM, we found that PaLM-2 models are able to identify most of the major errors. However, they tend to overpredict errors and have overall low span precision. Scale also seems to be important for the quality of spans produced by AutoMQM, with Unicorn outperforming Bison at most metrics. Furthermore, Unicorn prompted with AutoMQM predicts spans of comparable quality to those produced by current state-of-the-art learned word level evaluators, despite only leveraging a handful of annotations.